Yeah, now when we are getting into a generalized linear modeling kind of a mechanism, apart from the different distributions of the response variable, we also require two important aspects, which is the link functions as well as the linear predictors. We'll talk about what each one of them. But try to understand the concept of regression on a very broader note. See, we are trying to build a relationship between the response variable and a set of predictor variables which are my covariates. And if we see, the way we are generally building it is through this expected value of y kind of a function. For example, try looking at a simple linear regression where we said y equal to a plus bx plus some error term. Yi is a plus bxi plus some ei. Now if I look at this, right, what is the expected value of y here? It is nothing but a plus b times the expected value of x. And the variance is coming out, ei is the error term which is normally distributed with a mean 0 and variance equal to sigma square. So my expected value here is purely coming out as a plus bx, and whereas the variance is coming out through this. So it's as good as mu is a plus bx and the variance is sigma squared. So overall we are saying that the y is following a normal distribution with a mean mu and variance sigma squared. Now this is what is the typical thing. So this is where when we are trying to build our own generalized linear model, what we are simply saying is there are three important ingredients which I require. One, I need the distribution for the data, right? In many cases, if that data is normal, I'll take it as normal. Otherwise, it can go to any other distribution which belongs to the exponential family of distribution. So it could be a Poisson, it could be a gamma, it could be a binomial or a log normal. So I need to know the distribution of the data. Then I need to get into a linear predictor, which is typically denoted by a term called eta, which simply talks about, it's a purely a function of the covariates or my predictor variables. So in a typical linear regression where I talk about y equal to a plus bx, we simply yi equal to a plus bxi plus ei. My predictor variable eta is nothing but a plus bx. So this is a linear predictor. First of all, in the here it is linear in the parameters a and b, not in the variables a and b. So the linear predictor should be linear with respect to the parameters a and b. With respect to the covariates, it need not be linear. Covariates no need to be linear, right? So that's one kind of a function that we have to establish. We'll talk about them slightly in more detail. And along with that, I also need a link function which will connect the mean response to the linear predictor. So the mean response to the linear predictor is what we call as the link function. In general, we see that the thetas which we use in the exponential families distribution model, that is generally acting as the link function. If you remember, some function which is an exponential family function, if I can write its density function in the form of y theta minus b of theta divided by a of phi plus c of y comma phi, right? Now, whatever is this theta, that generally comes out as my link function. We'll discuss about it slightly in more detail. For different kinds of distributions, we may have different kinds of link functions coming up. But this is the one that is linking the mean response, which is expected value of y, to the linear predictor. So in case of a normal distribution, directly expected value of y is same as that of the linear predictor, because linear predictor here is a plus bx, even the expected value of y is a plus bx. So here it does not require any kind of a link function. Whereas probably if I am looking at my data being a Poisson distribution rather than a normal distribution, we see that the link parameter would be of the form of log mu. So instead of directly taking it as it is, we may have a link function which is linking the linear predictor with the expected value of the response variable. So in general, there is some function of the mean response, and that function is called as a link function. Now, by looking at all these things, we are getting something of the form that g of mu equal to some eta. So I am trying to establish as a mean of the dependent, dependent or the response variable. I am trying to bring in the linear predictor variable. So g is the link function and eta is my linear predictor kind of a variable. We require all these three. If I have to do a proper GLM estimate, all these three are very much required. And in reality, if I see regarding the first one, the distribution of the data, one is either known at the outset itself. So the distributions would either be known in advance, or I can very well try getting the best fitted distribution from the data, right? And the linear predictor, coming to it, we can very well choose according to what we think is more and more appropriate. What kind of variables we require? Do we have covariates, which are generally the quantitative variables? Do we have factors which are categorical kind of variables? Do we have kind of interactions between the various factors and the various variables? Based on that, we can come out with a linear predictor or a linear, based on that, we can come out with a linear predictor. There are not much of rules around it. We have to just play around with whichever one that comes out to be the best possible. And again, with respect to the link function, there is not something like one is the best, though obviously the theta would be the most appropriate choice for the link function. Again, there could be a different range of link functions that can be very well used. Now, what we will try understanding is a few important characteristics, let's say with the link functions, so that we can be slightly more well versed in the choice of them. The first thing is the link function should be differentiable as well as invertible. In order to fit a model, I need to see that the link function is differentiable as well as invertible. And there are number of functions that could be more and more appropriate. But what we generally, number of functions that could be more and more appropriate as link functions. But for each distribution, whatever was the natural link function or the typical canonical link function, as I call it, is nothing but where we are seeing g of mu as the theta of mu. Theta is the one that is coming from the natural parameter. Theta is my natural parameter as a part of the exponential family of distribution, which means when I am considering my response variable is following more and more of a normal distribution, then mu is my link function. When I am considering a Poisson distribution, log mu is my link function. When I am looking at binomial, the logit, which is log mu divided by 1 minus mu, is my link function. When I am looking at gamma, the inverse or the reciprocal, wherein 1 by mu forms my link function. So these link functions, they work well for each of the above distributions. Though I can use I can use log mu as a link function for gamma. I can use 1 by mu as a link function for Poisson. I can do all these things, but it becomes slightly, I can use them, but the basic implications I need to be very much careful about before using them. But when I'm using the typical natural parameter itself, it could be quite simpler. And then moving on to the understanding of the linear predictor, here as I said, all the covariates, here this is where I look at all the covariates that are entering the prediction through this linear predictor only, right? So probably I can have different kinds of variables. So either covariates or factors. Here I can look at something which are more quantitative in nature, something which are more categorical in nature. And let's say if I am having a age as the predictor, which is more in terms of a quantitative terms, then all I can bring out is my linear predictor could be beta naught plus beta 1 x, where x is the age. But if I say I'm also going for gender as one more linear predictor, wherein I may have two different values, one for male, two for female. If that's the case, my model can become, instead of beta naught, I'll make it as alpha I plus beta 1 times x. Now alpha I can become 1 in case of a male and 2 in case of a female. I can become 1 in case of a male, 2 in case of a female, which means I'll have a different alpha 1 and different values for alpha 1 and alpha 2 and beta 1, which is based on the x. Now if I really want the beta, the parameter for x, also to depend on this, which means I'm looking at the interaction between the age as well as gender also, then it's better that I have different betas for different genders. So my model can become, my linear predictor can become alpha I plus beta I times x. So I can change my linear predictor in that kind of a mechanism, right? So whenever we are talking about the covariates, one, they can have an impact on their own, or they can talk about interactions with other covariates. If they are having an impact on their own, we are calling it as a main effect. Otherwise, we are calling it as an interaction effect. So wherever we are looking at the interaction between age and gender, we are typically calling as age multiplied by gender kind of stuff. So even this can have an impact on the response variable. And when I am including something like this, I have to include both the main effects, both the age as a main effect, gender as a main effect, I can create as a part of the model, which means I can very well build it as alpha I plus beta j plus gamma ij. the interaction between the age as well as the gender. So all these different kinds of mechanisms I can create as a part of my linear predictor. Suppose if I say, okay, age is my only linear predictor, or age is the only variable on which I want to build my model, then my linear predictor could be of the form beta naught plus beta 1x. But if I say, oh, gender is the only one that is my dependent variable, then I'll call it as alpha I. If I'm saying both age plus gender, both of them are my dependent variables, then I'll look at it as alpha I plus beta x. If I'm saying age plus gender plus the interaction between age and gender, this is where I can look at alpha I plus beta j times x. So depending on what I am considering as my link, what I am considering as a part of my variable, which are going to impact my response variable, I can very well consider my linear predictors in an appropriate manner. So at any point, an actual value, if it is entering the linear predictor, a factor is a parameter for each level that that parameter can take. So the scope of that linear predictors is quite wide. Whereas on the simplest model, what I can very well look at is a straight line kind of a model like this. But it can have different kinds of polynomials. I can very well say age and age squared can have an impact on my response variable. If that's the case, I'll simply build it as beta naught plus beta 1 x plus beta 2 x squared. So in x there could be a kind of non-linearity, but the parameters are linear in nature. Right, now I can have probably let's say I'm looking at two different covariates, age and duration. Then all I am building up is beta naught plus beta 1 x1 plus beta 2 x2. Now all these things, what we are trying out is, these are the different ways in which I can come out with my linear predictor once I know what are the predictor variables, covariates or factors which are going to impact my response variable, and based on that trying to come out with the appropriate linear predictor and the link function along with the response, along with the distribution of the response variable, which will help us in doing a generalized linear modeling predictions quite effectively, right?